In the theory of relativity, time dilation is a difference of elapsed time between two events is measured by observers either moving relative to each other or differently situated from a gravitational mass or masses. An accurate clock at rest with respect to one observer may be measured to tick at a different rate when compared to a second observer's own equally accurate clock. This effect arises neither from technical aspects of the clocks nor from the fact that signals need time to propagate, but from the nature of space-time itself. Overview. Clocks on the Space Shuttle run slightly slower than reference clocks on Earth, while clocks on GPS and Galileo satellites run slightly faster. Such time dilation has been repeatedly demonstrated, for instance by small disparities in atomic clocks on Earth and in space. Even though both clocks work perfectly, the laws of nature are such that time itself will bend due to differences in either gravity or velocity, each of which affects time in different ways. In theory, and to make a clearer example, time dilation could affect planned meetings for astronauts with advanced technologies and greater travel speeds. The astronauts would have to set the clocks to count exactly 80 years, whereas mission control, back on Earth, might need to count 81 years. The astronauts would return to Earth, after their mission, having aged 1 year less than the people staying on Earth. What is more, the local experience of time passing never actually changes for anyone. In other words, the astronauts on the ship as well as the mission control crew on Earth each feel normal, despite the effects of time dilation. With technology limiting the velocities of astronauts, these differences are minuscule. After 6 months on the International Space Station, the astronaut crew has indeed aged less than those on Earth, but only by about 0.005 seconds. The effects would be greater if the astronauts were traveling nearer to the speed of light, instead of their actual speed, which is the speed of the orbiting ISS, about 7,700 meters per second. Time dilation is caused by differences in either gravity or relative velocity. In the case of ISS, time is slower due to the velocity in circular orbit. This effect is slightly reduced by the opposing effect of less gravitational potential. Relative velocity time dilation when two observers are in relative uniform motion and uninfluenced by any gravitational mass. The point of view of each will be that the other's clock is ticking at a slower rate than the local clock. The faster the relative velocity, the greater the magnitude of time dilation. This case is sometimes called special relativistic time dilation. For instance, two rocket ships speeding past one another in space would experience time dilation. If they somehow had a clear view into each other's ships, each crew would see the other's clocks and movement as going more slowly. That is, inside the frame of reference of ship A, everything is moving normally, but everything over on ship B appears to be moving more slowly. From a local perspective, time registered by clocks that are at rest with respect to the local frame of reference always appears to pass at the same rate. In other words, if a new ship, ship C, travels alongside ship A, it is at rest, relative to ship A. From the point of view of ship A, new ship C's time would appear normal, too. A question arises. If ship A and ship B both think each other's time is moving slower, who will have aged more if they decided to meet up? With a more sophisticated understanding of relative velocity time dilation, this seeming twin paradox turns out not to be a paradox at all. Similarly, understanding the twin paradox would help explain why astronauts on the ISS age slower even though they are experiencing relative velocity time dilation. Gravitational time dilation. Gravitational time dilation is at play for ISS astronauts too, and it has the opposite effect of the relative velocity time dilation. To simplify, relative velocity and gravity each slow down time as they increase. Velocity has increased for the astronauts, slowing down their time, whereas gravity has decreased, speeding up time. Nevertheless, the ISS astronaut crew ultimately end up with slower time because the two opposing effects are not equally strong. The velocity time dilation is making a bigger difference, and slowing down time. The effects of low gravity would not cancel out these effects of velocity unless the ISS orbited much farther from Earth. The key is that both observers are differently situated in the distance from a significant gravitational mass. The general theory of relativity describes how, for both observers, the clock that is closer to the gravitational mass, i.e., deeper in its gravity well, appears to go more slowly than the clock that is more distant from the mass. This effect is not restricted to astronauts in space. A climber's time is passing slightly faster at the top of a mountain compared to people at sea level. As with all time dilation, the local experience of time is normal. In the situations of velocity time dilation, both observers saw the other as moving slower. Now, with gravitational time dilation, both observers, those at sea level versus the climber, agree that the clock nearer the mass is slower in rate, and they agree on the ratio of the difference. That is, the climber sees the sea level clocks as moving more slowly, and those living at sea level see the climber's clock as moving faster. Time dilation. Special versus general theories of relativity. In Albert Einstein's theory of relativity, time dilation in these two circumstances can be summarized. In special relativity, clocks that are moving with respect to an inertial system of observation are measured to be running more slowly. This effect is described precisely by the Lorentz transformation. In general relativity, clocks at a position with lower gravitational potential, such as in closer proximity to a planet, are found to be running more slowly. The articles on gravitational time dilation and gravitational redshift give a more detailed discussion. Special and general relativistic effects can combine. In special relativity, the time dilation effect is reciprocal, as observed from the point of view of either of two clocks which are in motion with respect to each other. It will be the other clock that is time dilated. In contrast, gravitational time dilation is not reciprocal. An observer at the top of a tower will observe that clocks at ground level tick slower, and observers on the ground will agree about the direction and the ratio of the difference. There is still some disagreement in a sense, because all the observers believe their own local clocks are correct, but the direction and ratio of gravitational time dilation is agreed by all observers, independent of their altitude. Science fiction implications. Science fiction enthusiasts have noted the implications time dilation has on forward time travel, technically making it possible. The Hafele and Keating experiment involved flying planes around the world with atomic clocks on board. Upon the trip's completion, the clocks were compared to a static, ground-based atomic clock. It was found that 273 plus or minus 7 nanoseconds had been gained on the plane's clocks. The current human time travel record holder is Russian cosmonaut Sergei Krikalev, who beat the previous record of about 20 milliseconds by cosmonaut Sergei of Dive. Simple inference of time dilation due to relative velocity. Time dilation can be inferred from the observed fact of the constancy of the speed of light in all reference frames. This constancy of the speed of light means, counter to intuition, that speeds of material objects and light are not additive. It is not possible to make the speed of light appear greater by approaching its speed towards the material source that is emitting light. It is not possible to make the speed of light appear less by receding from the source at speed. From one point of view, it is the implications of this unexpected constancy that take away from constancies expected elsewhere. Consider a simple clock consisting of two mirrors A and B, between which a light pulse is bouncing. The separation of the mirrors is L and the clock ticks once each time the light pulse hits a given mirror. In the frame where the clock is at rest, The light pulse traces out a path of length 2L and the period of the clock is 2L divided by the speed of light from the frame of reference of a moving observer traveling at the speed v relative to the rest frame of the clock. The light pulse traces out a longer, angled path. The second postulate of special relativity states that the speed of light in free space is constant for all inertial observers, which implies a lengthening of the period of this clock from the moving observer's perspective. That is to say, in a frame moving relative to the clock appears to be running more slowly. Straightforward application of the Pythagorean theorem leads to the well-known prediction of special relativity. The total time for the light pulse to trace its path is given by the length of the half-path can be calculated as a function of known quantities as substituting d from this equation into the previous and solving for delta t gives, and thus, with the definition of delta t, which expresses the fact that for the moving observer the period of the clock is longer than in the frame of the clock itself, due to relative velocity symmetric between observers. Common sense would dictate that if time passage has slowed for a moving object, the moving object would observe the external world to be correspondingly sped up. Counterintuitively, special relativity predicts the opposite. A similar oddity occurs in everyday life. If Sam sees Abigail at a distance, she appears small to him, and at the same time Sam appears small to Abigail. Being very familiar with the effects of perspective, we see no mystery or a hint of a paradox in this situation. One is accustomed to the notion of relativity with respect to distance. The distance from Los Angeles to New York is by convention the same as the distance from New York to Los Angeles. On the other hand, when speeds are considered, one thinks of an object as actually moving, overlooking that its motion is always relative to something else, to the stars, the ground, or to oneself. If one object is moving with respect to another, the latter is moving with respect to the former and with equal relative speed. In the special theory of relativity, a moving clock is found to be ticking slowly with respect to the observer's clock. If Sam and Abigail are on different trains in near light speed relative motion, Sam measures clocks on Abigail's train to be running slowly, and similarly, Abigail measures clocks on Sam's train to be running slowly. Note that in all such attempts to establish synchronization within the reference system, the question of whether something happening at one location is in fact happening simultaneously with something happening elsewhere, is of key importance. Calculations are ultimately based on determining which events are simultaneous. Furthermore, establishing simultaneity of events separated in space necessarily requires transmission of information between locations, which by itself is an indication that the speed of light will enter the determination of simultaneity. It is a natural and legitimate question to ask how, in detail, special relativity can be self-consistent if clock C is time-dilated with respect to clock B and clock B is also time-dilated with respect to clock C. It is by challenging the assumptions built into the common notion of simultaneity that logical consistency can be restored. Simultaneity is a relationship between an observer in a particular frame of reference and a set of events. By analogy, left and right are accepted to vary with the position of the observer, because they apply to a relationship. In a similar vein, Plato explained that up and down describe a relationship to the earth and one would not fall off at the antipodes. In relativity, temporal coordinate systems are set up using a procedure for synchronizing clocks. It is now usually called the Poincare-Einstein synchronization procedure. An observer with a clock sends a light signal out at time t1 according to his clock. At a distant event, that light signal is reflected back, and arrives back at the observer at time t2 according to his clock. Since the light travels the same path at the same rate going both out and back for the observer in this scenario, the coordinate time of the event of the light signal being reflected for the observer t is t equals 2. In this way, a single observer's clock can be used to define temporal coordinates which are good anywhere in the universe. However, since those clocks are in motion in all other inertial frames, these clock indications are thus not synchronous in those frames, which is the basis of relativity of simultaneity. Because the pairs of putatively simultaneous moments are identified differently by different observers, each can treat the other clock as being the slow one without relativity being self-contradictory. Symmetric time dilation occurs with respect to coordinate systems set up in this manner. It is an effect where another clock is measured to run more slowly than one's own clock. Observers do not consider their own clock time to be affected, but may find that it is observed to be affected in another coordinate system. Proper time in Minkowski diagram. This symmetry can be demonstrated in a Minkowski diagram. Clock C resting in inertial frame S meets clock A at D and clock B at F. All three clocks simultaneously start to tick in S. The world linear of A is the court axis, the world linear of B intersecting F is parallel to the court axis, and the world linear of C is the court axis. All events simultaneous with D in S are on the x-axis, in S, on the x-axis. The proper time between two events is indicated by a clock present at both events. It is invariant, i.e., in all inertial frames it is agreed that this time is indicated by that clock. Interval df is therefore the proper time of clock C, and is shorter with respect to the coordinate times f equals dg of clocks B and A in S. Conversely, also proper time f of B is shorter with respect to time if in S, because event E was measured in S already at time I due to relativity of simultaneity, long before C started to tick. From that it can be seen that the proper time between two events indicated by an unaccelerated clock present at both events, compared with the synchronized coordinate time measured in all other inertial frames, is always the minimal time interval between those events. However, the interval between two events can also correspond to the proper time of accelerated clocks present at both events. Overview of formulae. Time dilation due to relative velocity. The formula for determining time dilation in special relativity is, where delta t is the time interval between two co-local events for an observer in some inertial frame, known as the proper time. Delta t is the time interval between those same events, as measured by another observer, inertially moving with velocity v with respect to the former observer. V is the relative velocity between the observer and the moving clock. C is the speed of light, and the Lorentz factor is thus the duration of the clock cycle of a moving clock is found to be increased. It is measured to be running slow. The range of such variances in ordinary life, where Vc, even considering space travel, are not great enough to produce easily detectable time dilation effects, and such vanishingly small effects can be safely ignored for most purposes. It is only when an object approaches speeds on the order of 30,000 km per second that time dilation becomes important. Time dilation by the Lorentz factor was predicted by Joseph Larmor, at least for electrons orbiting a nucleus. Thus, individual electrons describe corresponding parts of their orbits in times shorter for the rest system in the ratio. Time dilation of magnitude corresponding to this factor has been experimentally confirmed, as described below. Time dilation due to gravitation and motion together, high accuracy timekeeping, low Earth orbit satellite tracking, and pulsar timing replications that require the consideration of the combined effects of mass and motion in producing time dilation. Practical examples include the International Atomic Time Standard and its relationship with the barocentric coordinate time standard used for interplanetary objects. Relativistic time dilation effects for the Solar System and the Earth can be modeled very precisely by the Schwarzschild solution to the Einstein field equations. In the Schwarzschild metric, the interval dt is given by where dt is a small increment of proper time t, dtc is a small increment in the coordinate tc, dx, dy and dz are small increments in the three coordinates x, y, z of the clock's position, and gmi, ri represents the sum of the Newtonian gravitational potentials due to the masses in the neighborhood, based on their distances ri from the clock. This sum gmi, ri includes any tidal potentials, and is represented as u. The coordinate velocity of the clock is given by the coordinate time tc as the time that would be read on a hypothetical, coordinate clock, situated infinitely far from all gravitational masses, and stationary in the system of coordinates. The exact relation between the rate of proper time and the rate of coordinate time for a clock with the radial component of velocity is where v is the radial velocity, and u equals gmi, ri is the Newtonian potential, equivalent to half of the escape velocity squared. The above equation is exact under the assumptions of the Schwarzschild solution.